pleased to introduce the speaker for this session, Mahesh Kailasam. Mahesh is the General Manager of the Design and Engineering Business Unit of Hexagon's Manufacturing Intelligence Division, covering their entire simulation portfolio. He joined Hexagon in September of 2019 and has been leading numerous strategic and transformational activities in D&E and across Hexagon Manufacturing Intelligence. Prior to Hexagon, Mahesh established and expanded Thornton Tomasetti's applied sciences business in life sciences. Before that, he contributed to growing the simulation business of Dassault Systemes via roles in various functions, including product development, product management, and business development for almost 2 decades. With over 25 years of experience in the CAE industry, Mahesh has an MS and a Ph.D. in mechanical engineering and applied mechanics from the University of Pennsylvania and a B.Tech in mechanical engineering from the Indian Institute of Technology, Madras. It will now be our pleasure to hear from Mahesh Kailasam.
Hello, everyone. I'm very pleased to have the opportunity to speak to you and tell you a little bit about what is happening with CAE and multiphysics simulations to make manufacturing more productive, profitable, and sustainable, with the ultimate goal of making significant progress towards smart and autonomous manufacturing. Most organizations have already embarked on a journey where they are using CAE for designing their products and making sure that those products will function well as intended, meaning from a product durability or from a product performance point of view. They often are incorporating multiple complex physics into their simulations. It could be fluids and acoustics, as you see in this case. It could be noise, vibration, and harshness assessments, as you see over here, or a couple thermal fluid flow assessments for thermal runaway avoidance simulations in electric vehicle batteries. I'm sure you're already familiar with many applications of CAE that help people imagine and design better products. In that sense, CAE has come a long way and has had and is continuing to help develop much better products. We've also been quite successful in taking advantage of modern computing capabilities and high-performance computing so that we can solve even more challenging problems that might require more sophisticated modeling. Might simply be large models or longer duration events or adding more physics. In this example, for example, this problem involves about 230 million elements and almost 200,000 cores. In this next example shown here, you can see the speed up we are able to get by leveraging GPUs in this case. So about a 5x speed up in this acoustic application. So pretty good overall, I would say. In fact, we have reached a point where we can take advantage of modern computational algorithms and implementation schemes to get to real-time simulations, where accurate physics-based models can provide real-time guidance on how a product or system is going to behave. This enables the use of simulation-based models to be used within various machines. And this is a point I will come back to in a bit as well, especially in the context of manufacturing. In this example, you're seeing Adam's RT multi-body simulations being used within a driving simulator in a realistic driving environment to evaluate ride handling and comfort. More recently, we have seen widespread adoption of generative design concepts to help develop designs that may not be intuitive, but can be really effective in meeting functional and other criteria, such as weight reduction. And even in this case, we've been able to take advantage of modern processors to significantly reduce design iteration times. So the point is that CAE has been very useful in helping various companies and multiple industries develop far better designs, make better choices on everything from material selection to deciding what performance characteristics matter most, and basically help come up with better products. And we are able to do all of that faster and much more efficiently thanks to high-performance computing. In the future, you'll continue to see improvements here and for us to obtain greater value from simulations with the adoption of techniques such as AI ML to improve the product development and product design processes. What I'd like to do now is to pivot to a different topic. What can you do when you have to leverage CAE even more and come up with a much better application of CAE once you have a great design? Can we do more with simulations? Basically, can we answer questions such as what you see on the stage? Can you make the product that you thought you wanted to make? How do you make it? Can you make it fast enough? Can you make it within budget? Can you make it with the quality expected? How can you be confident? How can you be confident that the products as designed can actually be made to address all of the product requirements? Now, it could be performance, life, or other characteristics, as well as meet other business requirements like cost, quality, and sustainability. How confident are you that you're making progress towards zero prototyping? These questions require us to go beyond concepts like design for manufacturing and requires us to take advantage of simulations beyond the traditional product design and development space and to take it into the manufacturing space. The essential idea here is that our software and other simulation software already help design products that will function well as intended. Again, it could be the life or the performance, etc. But we don't need to stop there, and we shouldn't stop there. We can help select and evaluate the best manufacturing sequences that will be appropriate for a given product. It could be forming, cutting, welding, additive manufacturing, etc. A lot of which we can simulate with our software today. But we can go beyond that to tie together much more closely design and engineering, production, and metrology by leveraging such paradigms as AI, cloud, data integration, and workflow management. For example, once you have confidence that products can be made properly, because you've evaluated it via virtual manufacturing simulations, we can then continue the journey by providing simulation-based guidance during the actual manufacturing to adjust process parameters, such could be speed, temperatures, and so on the fly based on measurements so that the products still come out as intended, or to flag situations where manufacturing needs to be stopped for corrections. We expect that our AI/ML technologies, in conjunction with our manufacturing simulation solutions, to play a key role here. We can also go beyond that to provide simulation-based guidance for quality checks that might need to happen during actual manufacturing. For example, what are the critical quantities to measure, where to measure them, how often to measure them, and so on. After a part has been manufactured, simulations can continue to provide value by providing insights into the behavior of the as manufactured parts. Will the porosity distribution affect the life of the part? Will a slight deviation in dimensions cause premature failures, and so on? At each stage, there are feedback loops that allow for continual design, engineering, and manufacturing improvements. This is the essence of smart manufacturing, at least our promise of it at Hexagon. Now, in order to realize this promise and potential, there is one key piece that needs to be considered: measuring what's happening in the real world, and not just living in the simulation or the virtual world. This connection in both directions between the real and the digital worlds is essential to realize the promise of smart manufacturing, and is at the center of what we do at Hexagon, not only for manufacturing, but to provide autonomous systems in various application areas, and to realize what we call smart digital realities. So what are smart digital realities? Smart digital realities are real-time 3D digital worlds that are data-rich and autonomously intelligent. They're made possible by integrating sensor and software systems that connect customers on a one-on-one basis in a precise manner to 3D replicas of physical workplaces, objects, and processes. Smart digital reality is what allows us to move industry beyond automation to autonomy, providing the ability for systems to act independent of human interaction. So smart manufacturing is a manifestation of the smart digital reality when it's applied to the manufacturing space. Let's take a quick look at what all of this means using some examples. Consider the design and manufacturing of electric vehicle batteries. First of all, as we discussed at the beginning, we already can use simulations to design better batteries. These could be for battery cooling systems, as you see on the slide over here. It could be for modal analysis to prevent structural or other noise-related challenges. It could be for fatigue analysis, fatigue assessments to ensure adequate life the product, and so on. We can also assess how to make various parts of an EV battery and how they're going to come together. So in the case of a battery pack, now the battery is composed of cells, modules, and of course it requires a battery pack and a tray, and that are assembled together. So in addition to making these individual parts of the EV battery pack, you can see in this short video that we also need to consider assembly that involves various types of mechanical fastening, gluing, welding, and other types of connection mechanisms. So I'll just let the video play for a few more seconds so that you get a sense of how many different types of connections and assembly mechanisms are used in the assembly of an electric vehicle battery pack. So that takes us into the world of virtual manufacturing, where we are able to simulate in detail how various parts of the battery would be manufactured, and which methods are used, and what would the process parameters be to ensure that the final product quality would be good. You can see some examples of virtual manufacturing simulations here when it comes to different parts of the electric vehicle battery. So for example, you can look at stamping the cap, rolling the cap, and welding the tab. And here are some more examples of cold forming and lid stamping. Clinching the terminals, welding the lid, and so on. So now let's move from the virtual world to the real world. In the virtual world, as we have seen, we can use simulations to design the battery and its various parts. And we've also used simulation to virtually manufacture the various parts to assemble it. Now, what does that mean in the real world? This is where things get really exciting. We can take the process parameters for welding, for example, from simulations, could be weld speed, temperatures, and so on, and use that information to program modern automated robotic welding machines, such as the one you see here from ESA. Not only that, we can embed simulation-powered intelligence derived via AI/ML techniques into the machines so that if process parameters differ from ideal conditions, for example, if parts or fixtures are warped or if the torches are bent and so on, the machine can still make adjustments autonomously, which is a big step forward towards smart manufacturing. In some EV batteries, there are hundreds of cells per module and over several thousand cells in many modules. That results in tens of thousands of welds in the assembly. So even at 99.9% or higher weld quality, safety and range could be compromised. So welds must be studied and tested for higher quality in production. In other words, both precision in manufacturing and precision in inspections are paramount. So in the real world, as the manufacturing is proceeding, we still need to measure what is being manufactured so that adjustments can be made as soon as possible. Are the dimensions correct? Are there microstructural defects? Is delamination happening? And so on. And just as we saw with the welding machines, here again, simulation can play a valuable role by providing guidance into what are the most important quantities that need to be measured. Where do they need to be measured? How often do they need to be measured, and so on. Measurement routines can be planned based on geometry, but also based on guidance from simulations so that the scanning routines can be optimized. Finally, the output from these measurements can be compared to nominal quantities for key decisions to be made. Let's take some more examples of what measurements can tell us about the quality of battery parts as they're being made. This is an example of optical measurements of wrinkles in pouch cells. Switching to CT scans, we're able to look inside some of the battery parts, such as the cathode, for porosity, particle size, and other details. Or we could look at inclusions in a jelly roll, delamination, porosity effects, and so on. So what do we do with these measurements in the real world? This could be, again, dimensional measurements or microstructural measurements or other characteristics. Well, first of all, as we just discussed, wherever possible, we could use those measurements if they're happening during manufacturing to adjust the manufacturing process parameters, guided again by simulation-based intelligence so that the quality of the products are not compromised. We can also use those measurements to understand the behavior of the as manufactured product for reality-based simulations, but of course for other analytical assessments using various quality and statistical methods applied to numerous measurements being made. So to conclude, we need to go beyond the traditional use of simulations in design and development of products in order to help realize the potential that smart manufacturing offers. The use of virtual manufacturing simulations will enable earlier decisions on the manufacturability of various product designs and provide greater confidence in the progress towards zero prototypes. The use of simulations-based intelligence within manufacturing and measurement machines will also ensure that appropriate degree of autonomy and self-corrections are available during manufacturing to accommodate stuff that happens in the real world without compromising on product quality. All of this is essential to enable autonomous and smart manufacturing. So simulation will play a key role in our journey from where we are today towards our destination of smart manufacturing. Thank you.